Hello and welcome. In this second part, we will be going over the last points, 5 and 6, which is the actual implementation and testing of the proportional action and integral action. I assume you have already watched the first part, that's why I will not go over again all the details. If you want more details, please refer to part 1. So, what we are going to do now is actually implementing the proportional action of the PID control. If we remember, the proportional action, that's the actuation that we will introduce for the control, is equal to the error multiplied by a constant of proportional action. This constant is a constant that we have to adjust seeing how the system behaves. We can adjust it during testing. And for the error, it is defined as the difference between the target value and the current value. In the last part of the last video, we defined how we were going to set the target value. So basically we have a couple of buttons that allow the user to set the target value that he wishes, the height that he wishes to have in the tank. So that's already set. As for the current value, we are going to read it from the height sensor. Finally, the voltage that we are going to actually write on the filling valve will be the equilibrium voltage plus the proportional action thus defined. So first of all, we are going to tackle the issue of reading and writing the variables, because if you remember, the connection schematics were as follow. So we are not really connected to the actuator valve and the reading sensor. Rather, we are doing it through a Modbus device. That's why we have to set up Modbus communication. Again, I have a couple of videos of how to do that. Here I'm just going to set the variables. So for that, in Arduino PLC IDE, we would go to Ethernet and we would create a new generic Modbus device. This device represents the PLC that is in the lab, to which we have plugged the sensor and the motor, the actuator for the filling valve. This new device that we generate, we can give it a name. Here I have named it Water Tank PLC, and we must give it an IP address. That's the address of the slave. Also a Modbus address, which is the number, whichever number you want, but it must be the same, obviously, at the PLC that is receiving, is the slave. Then we create, in this menu, if we click by the right button and add, we will have this window here where we can add functions for reading and writing. We are interested in two functions. Function 4, which is able to read a register on the slave PLC. That's what we will use to read the water height. And function 6, which is a function that is able to write into the slave PLC. So that's how we will set the value, the voltage value that we wish to have in the filling valve. So in order to set up the read function, as I say, we create here a function 4. We give it an address. This is the address that this register has on the slave device. In this case, it's 2. And we give it how often we want this reading to be done. So we have it here as 4 times a second. And then if we click on input registers, we can create a variable. So here I have created the variable tank current unsigned int. So in this variable, we will automatically get every 250 milliseconds the current height of the water tank. So that's the variable that we will use for our operations. We do the same for writing register. So this is the variable, this is how we will write the actuator into the actuator, the value that we want, the voltage that we want. Again, we create another variable, and in this variable, which I have called tank send int, is where we will write the voltage that we want to have on the actuator. Then I've gone to functional block diagram and I have created a couple of lines. So first line is the calculation of the error. The error is the difference between the target value and the current value. So I have created a difference. Target level centivolts, we have described it in the previous video. That's the variable where we have stored the target height that the user wishes to have. And then we have target current, which is the reading of the sensor. The difference between the two is the error. Then we have the proportional action, which, if we remember the definition, is the multiplication of the error multiplied by a constant. In this case, this constant, I have given it the value 1.3, but again, you can adjust it however you want. Then I have created a couple of lines here, and they are just there to cap the maximum and minimum value of the proportional action contribution. So no matter what happens, I have decided that I don't want the action to be any lower than minus 1.3 and nor any higher than 1.3. This is with respect to the equilibrium value. And finally, this is how we are going to write the actual voltage that we're going to send. It will be the addition of the equilibrium value plus the proportional action. The equilibrium value, we saw in the last video that it was 2.3 volts. And then the proportional action is calculated as I explained earlier, which is a constant multiplied by the error. And in any case, it will be between minus and plus 1.3. So actually, the values that we are going to be sending into the actuator will be 2.3 plus or minus 1.3. So it will be between 1 volt and 3.6 volts. That's the voltage that we will be allowed to send. And we are ready to go. So to sum up this part of the proportional control, with a couple of buttons we can set the target value, the current value, we're reading it through this input register that is connected to the tank. The proportional action is calculated as the error multiplied by a constant that we can adjust later. And finally, the valve voltage that we're going to write into the valve is the addition of the equilibrium voltage, which we had discovered it was around 2.3 volts, plus a proportional action that we have decided to limit between minus or plus 1.3. So let's test it. Okay, so now let's test the system and see how it controls. Right now we have set a target level of 1.57 meters. This is the value in centimeters and this is the value in millivolts. So we have 5.28 volts that we wish to read on the height sensor, and what we are actually reading on the height sensor is the same value. So first of all, we are going to introduce a perturbation and see how the system corrects, the proportional control corrects this perturbation. So first of all, let's introduce the failure. So let's imagine that we introduce an uncontrolled amount of water and then we leave the system to correct itself. So right now the proportional action is negative because it's reducing the value with respect to the equilibrium value while it tries to level back to the equilibrium target. So we can see that it corrects, and as the difference between the target level and the actual level gets smaller, the proportional action also gets smaller, and the correction is pretty smooth. So it looks pretty good that it's able to correct, albeit a little bit slowly. So now let's, for example, set a different target height. So let's imagine that instead of 157 centimeters, we want the tank to be a little bit higher. Let's say 177. So you can see now that the proportional action is higher than 0 and that the water level is slowly rising until it reaches the 1.77 value, more or less. However, you can see that as it nears the target value, it also slows down until a point where it doesn't really reach the target value, and that's because we don't have an integral action. This effect is more extreme if we are far from the equilibrium point. So for example, if we try to introduce a much higher height, so let's put like 2.14 meters. So right now the system will raise, but eventually you will see that we cannot really reach this value, and that's because the losses of water are higher than the system knows. So normally we should approach it, but there will be a gap on the, so our actual value will be a little bit below the wish value of 2.14 meters. And here you can see that the reach value is about 2.06. We don't really reach the 2.14. That's because we are far from the equilibrium point. So if we now target another value which is close to the equilibrium, we should get a better value. So let's reduce it to 1.55, and let's wait a little bit. And again, you can see that the value, it is not exactly reached, and eventually there will be a very small gap between the target and the real value. Finally, let's see how the system behaves when we target a target point which is far from the equilibrium zone and very, very far below. So let's reduce it, the target height, down to, for example, 57 centimeters. So let's wait a little bit. Okay, so when we try to reach a value of 57, you can see that the level is descending, but the descent is very, very slow. That's because the closer we are to the target value, the smaller the proportional action is. And since we are far from the equilibrium point, the control is not really good, and this there is not a tool to correct this. This kind of final positional errors are very well corrected through the integral action. So that's what we are going to explore next on the video. Let's introduce the integral correction. Okay, so let's now talk about the integral action. These are the definitions of the different actions of the PID control. The proportional action we have already described. It's a constant multiplied by the current error. And now we're going to talk about the integral action. So for that, what's defined here is that it's an action that increases the longer the error persists. So for example, if there is an error that we have, like the water level is not really reached, and this situation continues for a long time, then the integral action will reinforce itself in order to correct this permanent error. So the definition says that it's defined by a constant for the integral action multiplied by the integral of the error over time. If we try to implement this idea into PLC IDE, we can see that among the operators that we have, we do not have an integrator like we would have, for example, in Simulink or any other program where we could have an integrator for time. Here we do not have it. However, this is such a simple concept that in fact we don't really need a dedicated function. We can do it just with multiplications and a timer. I'm going to show you how. So if we transition the idea and express the integral instead of the theoretically perfect addition of infinitesimally small points, we can just do it as a sum of discrete points. So, for example, if we have the error over 3 instants, in order to do this integral, it will be more or less the same as saying the constant multiplied by the error in the first moment multiplied by an increment of time, plus we wait until the next moment, we evaluate again the error, and we repeat the multiplication. And then we wait for the next moment, and we evaluate the error, and then we repeat the multiplication. If we keep the delta time constant, it's just a timer in practice. So how does this look? Here, what I have implemented is a ladder diagram with this operation. So I'm gonna describe it. First of all, in the first line, what we have is a timer of, in fact, 400 milliseconds. So I'm going to be doing this step, this addition, every 400 milliseconds. So in the first line, we just have a timer that can be reset. If the reset is not pressed, this timer is on. So when the program starts, this timer will start to count until 400 milliseconds. When the 400 milliseconds are reached, the queue, the output is enabled, and the time elapsed value is set to 1. So this tells us 400 milliseconds have passed. Do your operation. That's what the second line does. If this time has passed, first of all, we do the multiplication of the error in this instant multiplied by the increment of time multiplied by the constant of integration. This constant we can set however we want. However, the time should coincide with the time of the timer. So we do this multiplication, and then we add it into wherever the integral action already was. So in effect, we have a variable where we continually store this multiplication here. That's pretty much it. Then we reset the timer so that the next step can begin. And we also reset the variable that tells us that the time has already passed. And then this is done again and again and again. So every 0.4 seconds, this multiplication is performed and the value is stored in a variable. So that's the integration. Okay. Next, I have added a couple of functions which in a functional block diagram that just serve to cap the integral value. This is because if the integral value, or if the system is very slow, then the integral value can accumulate and accumulate and accumulate, and then you will overshoot your target. So in order to avoid that, I have just capped the value that the integral action, so this whole operation, the maximum value this whole variable can have. That's optional. I have just chosen to do it. And finally, here when talking about the voltage that we send into the actuator, it now has 3 contributions. It has the equilibrium voltage, which was 2.3. It has the proportional action, which is a constant multiplied by the current error. And then it has the integral action, which is calculated as we have described, and which is capped at 0.35 volts. And that's pretty much it. So let's test the system and see how it goes. Okay, so now let's test the system, but with the integral action included. You can see that in the value that we actually send into the valve, we have 3 contributions. We have the equilibrium value, the proportional action, which is very small because right now we are very close to the target value, and the integral action. And here we can see, we can track the target level in centimeters and in centivolts, and then the current tank height. So for example, let's target a higher value than now. So let's put, for example, the maximum that we have capped, which is 2.14 meters. And let's see how this controls. So right now you can see that the proportional action at the moment is the maximum because the distance, the error is still high, and also the integral action is high. What we will see as the system, as the level approaches the target level, is that the proportional action will be decreased as it's doing now, but the integral action will remain, in fact, until the level has been reached. Then the error will switch sides, and only then the integral action will diminish. So that's why this component helps at least reaching the target value, unlike before, where if we remove this contribution, just with the proportional action, we will be unable to reach the target height. See that now, it seems that we're going to be able to reach it, or at least come closer than before. So yes, it looks like we will be able to reach the 720 value. And then at that point, see that right now all the contribution is the integral action. The proportional action is contributing very little into the total 2.67 volts that we are right now sending into the actuator. And we seem to be able to at least reach the target value. Okay, so now let's target a value which is close to the middle, to the equilibrium area. So in that case, we should be able to get there, no problem. So let's target, for example, 1.65 meters. And we can see that right now the integral action has reversed signs. And we seem to be on the way to reaching this target value. So let's see how this behaves. Okay, so we are approaching now. See again that the proportional contribution is very little, and the main contribution is the integral action. As we switch signs, we are right now overshooting, because see that we are still descending even though we are below the target value. But this should very fast correct as the integral action switches signs, and then we will approach much closer the target value. So you can see now that we look good to be able to reach the value, and the overshoot will be inferior. If you play a little bit with the parameters, with the cap of the integral action and also with the integral constant, you can adjust it so that it goes a little bit better. And finally, let's target a very low value as we did before, whereas before we couldn't really reach it. Let's see what happens now. So I'm gonna descend it down to 57 centimeters, for example, and let's see what happens. Okay, so what we can see now is that, again, the system seems to have some difficulty in reaching the target level of 57 centimeters, although less so than before. At this point, it's just a matter of adjusting the parameters, so that you should adjust the proportional and integral constant, as well as the saturation values that we had, particularly on the integral, because right now it's set at -35. But it obviously needs to be a little bit higher so that it can compensate the positional error that exists right now. But again, as I say, it's just a matter of adjusting. So I'm gonna end the video here. I hope that with this video you have a clear picture of how you can do PID control by using the Arduino OPTA. Thanks for watching.